Assalamu alaikum class. I hope that all of you are well and safe in your homes inshallah. For lecture 26, we'll be concluding our discussion of Laplace transform. So we'll be going over all the key concepts that we discussed from lecture 19 to lecture 25, and in the end the concept of Laplace transform would be extended to see what are the application areas where Laplace transform can be used. The concept of Laplace transform was devised by a French mathematician and is named after him, Pierre Simon de Laplace, in the year 1779. In our course, we are going to study bilateral Laplace transform, which is that for a function f of t, if we want to determine its Laplace transform, we integrate the function between the limits from minus infinity to plus infinity and multiply it by an exponential e to the power minus st. Laplace transform is a bidirectional transformation, which means that if a function f of t has a Laplace transform f of s, then the same f of s will give us f of t after taking the inverse Laplace transform. While the basic definition of Laplace transform is known as a bilateral Laplace transform, is because as we can see that the limits of integration are from minus infinity to plus infinity. In our book as well as in several other textbooks, unilateral Laplace transform is also introduced, where the limits of integration are from 0 to infinity, and the relationship of unilateral Laplace transform with bilateral Laplace transform is explored. But for our course, we'll be seeing a bilateral Laplace transform only. So what Laplace transform does is that it changes a time domain function into an S-domain function. But what is S-domain? Well, we'll see that S is a complex variable. It has a real part, which is sigma, and it has an imaginary part, which is g omega. So since it is a complex variable, it can be represented by a plane, two-dimensional plane, which is an S-plane. So the real part of S is plotted along the x-axis, and the imaginary part of S is plotted along the g omega axis. And just like all two-axis planes, we'll be having four quadrants where sigma and omega will be positive in some quadrant and negative in some other quadrants. Now whenever a function f of t gives us a Laplace transform f of s, the f of s might have a rational form. So in this rational f of s, the roots of the numerator and denominator have different meanings. The roots of the numerator for f of s are the values of s where f of s becomes 0. So they are known as a 0 of f of s. The roots of the denominator of f of s are the values where the value of f of s gets infinite. So they are known as the poles of f of s. So if I plot this f of s, the magnitude of f of s versus real s and imaginary s, that is if we make a 3D plot, then we can see that the values, this plot, if you see f of s this is dB, the magnitude is in decibels. So the values of where f of s, where the magnitude is too high, gets out of range, is a pole of f of s, and the value where we see a dip is the 0 of f of s. If we have the poles and zeros of f of s with us, then debarring or keeping a multiplier factor aside, f of s can be completely described by a description of its poles and zeros. So we just discussed that Laplace transform is a mathematical tool which converts a time domain function into an S domain function, whereas S is a complex variable. So the time domain function is converted into an S domain function by multiplying the time domain function by an exponential e to the power minus st and integrating the function between certain limits. So does the value of f of s exist for all values of s? No, it is not, because the exponential e to the power minus st is only going to give us a finite value within a certain range. So all the complex values of s for which the integral in the definition converges, they form a region of convergence. So the definition of Laplace transform will give us a value for Laplace transform f of s along with the region of convergence. The value of Laplace transform is not complete if the region of convergence is not specified, because the region of convergence is the range in which we are getting those values. So the Laplace transform along with the region of convergence, the magnitude along with the region of convergence, gives us a very powerful mathematical tool. Using this mathematical tool, the Laplace transform, we can solve many complex mathematical problems through simple algebraic operations. So difficult mathematics becomes simple. So Laplace transform is an analysis tool. It is also a design tool because it simplifies. We'll be seeing, and we have we did see that many mathematical operations were simplified by using Laplace transform. So this region of convergence we discussed, it had certain properties. What were the properties of ROC? First of all, the ROC does not contain any poles. So for f of s will not have any poles. The ROC is exclusive of poles. If we have a finite duration signal, the ROC is the entire S-plane. If we have a left-sided signal, the ROC was inside the innermost pole. If we have a right-sided signal, the ROC is outside the outermost pole. A right-sided signal is a signal which starts at or greater than time t is equal to 0. And a left-sided signal is a signal which exists for time less than 0. If it's a both-sided signal, that it exists between a certain range of time from which covers minus time values as well as positive time values. So if the signal f of t is a two-sided signal, then the ROC is a ring which is bound by the poles. We discussed that ROC is a connected region, so it must always be connected. Then we discussed Laplace transform of some elementary functions. Table 9.2 of your book, I have just paste the table, and from property, I've just used those values of signals which we used more in this course. So we saw that if we had a signal del of t, which was an impulse, the Laplace transform was 1. For a unit step function, the Laplace transform was 1 by s. And this is a right-sided unit step function. In case we notice, it's a right-sided signal. So the Laplace transform is 1 by s, but since the pole is at s is equal to 0, and it's a right-sided signal, so a dl of s is greater than 0. Minus u of minus t also has the same Laplace transform, which is 1 by s, but now since it's a left-sided signal, so the ROC is less than the pole, which is VLS is less than 0. Similarly, we can see for all this table that there will be some signals which will be having the same Laplace transform, but will be having a different region of convergence. So that is why the value of Laplace transform along with the region of convergence gives us the full expression for the Laplace transform of a signal. This also, the Laplace transform along with the ROC, can also give us information about the type of signal, that whether it was a left-sided signal or a right-sided signal or two-sided signal, etc. Laplace transform is a bidirectional transform, which means that if f of t has a transform f of s, then given f of s and the ROC, we can determine the inverse Laplace transform. In our course, we use the method of partial fraction. So the complex f of s, the complex rather rational, if it's a rational algebraic expression, it is broken down into a linear combination of lower order terms, and for each of these lower order terms, the inverse Laplace was determined by inspection. How did we inspect? How did we inspect? We were given table 9.2, or we remember formulas, and we compared the functions, the f of s, with the time domain functions, and we came at a conclusion. For the inverse Laplace transform, we saw several cases. We saw the cases for the rational function where the roots of the denominator are distinct for the partial fraction. We saw the situation where the roots were complex, and we saw if the roots are complex, then they must exist in conjugate pairs. And we saw the third situation, where we have multiple roots at the same location. So we saw all these situations when we discussed how to determine the inverse Laplace transform for each of this case. Also, for the inverse Laplace transform, we need the ROC. What if we don't have the ROC? Then we have to probe or explore all the cases. For example, we are given f of s is equal to 1 by s plus a, which means that the root or the pole is at s is equal to minus a. Since we don't have any information about the ROC, so for inverse Laplace, we'll consider both cases. That is, if real s is greater than minus a, which is a right-sided signal, and if the real s is less than minus a, which is a left-sided signal. So we have to explore all cases, and this might make more than two combinations. We have done some problems where the ROC was not mentioned, and we saw three regions. In our course, we are using Laplace transform as a tool to analyze systems, particularly linear time invariant or LTI systems. So we discussed some properties of Laplace transform. From these properties, it was easy for us to analyze systems. The properties we discussed in the course are linearity, time shifting, shifting in S domain, differentiation in time domain, differentiation in frequency or S domain, integration in time domain, and convolution. I told you that these are not all those properties which exist for Laplace transform. In fact, in your book, there are several other properties mentioned as well. But these properties are what we'll be discussing for our course, Signals and Systems. So I have emphasized on these properties only. All of these properties had some effect on the region of convergence, where in some cases the ROC was not changed, and for some cases the ROC was changed. The results are summarized in table 9.1 of your book. I told you that whenever you are using those tables, you have to understand what is the meaning of ROC. For example, for the linearity property, we saw that Laplace transform is a linear operation. So the Laplace transform for a sum of several functions is equal to the sum of individual Laplace transform for each of these functions. But what happens to the ROC? The ROC is the intersection of all these ROCs. Similarly, for other properties, the ROC was affected, and if you don't recall them right now, you can go through that lecture again to see what was mentioned. But from these properties, we saw that there was a symmetric pattern between the time domain, functions, that is signals, and the frequency domain, the Laplace transform. For example, we saw that differentiation in one domain, for example, differentiation in time domain, corresponds to multiplication by a variable s in the frequency domain. Similarly, differentiation in the frequency domain corresponds to multiplication by t in the time domain. So there was a similarity. Multiplication in one domain implies differentiation in the other domain. Similarly, multiplication by an exponential in one domain corresponds to a shift in or delay in the other. Or if there's a shift in time domain, that means that in the s domain we have a complex exponential appearing. Or if we have a shift in the s domain or the spectrum frequency domain, then there's a multiplication by an exponential in the time domain. So these similarities were observed. So in case you don't remember the properties, or if you're not given the table, for instance, you can recall or you can say that this is what happens. So Laplace transform is going to be used as a tool to analyze LTI systems. For an LTI system, we know that if an input x of t is applied to the LTI system and we get the output y of t, then the system is governed by its impulse response or h of t. So whenever x of t is convolved by h of t, we get our output y of t. Using property of convolution, this formula or this system can be simplified in the transform domain as given input x of s multiplied by the system function h of s, we get our output y of s. So h of s is the transfer function or the system function, and it's a ratio of y of s to x of s using the convolution property. An LTI system can be mathematically specified through three relationships: the system differential equation, linear constant coefficient differential equation, the system transfer function h of s, or the system impulse response h of t. Given any one thing, we can convert into other two forms using the properties of Laplace transform. We used Laplace transform to analyze LTI systems using the property of convolution. So we saw that if we have, say, x of t and h of t given, we can determine y of t. If we have x of t and y of t given, we can determine h of t. If we have h of t and y of t given, we can determine x of t. So we could determine anything given the other two parameters by using the Laplace transform form, that is the product of two terms, these two terms giving the third term. We have to be conscious about the ROC, and we saw it through several examples that how can we cater for ROC. Also, we used differential Laplace transform to solve differential equations, and we saw that the complex process of calculation of solution for a differential equation, which was a three-step process, was converted into a simple one-step process by just taking the Laplace transform and inverse Laplace transform, and we got a complete solution. For both convolution and differential equation solution, the time domain function was mathematically complex and cumbersome, involved a lot of steps, whereas for if we just transform the functions available to us into frequency domain or S domain functions, and we do the mathematics and take the inverse Laplace transform, the process becomes simpler mathematically. However, in all of these cases, we have to be conscious about, whenever we take the inverse Laplace transform, we have to be conscious about the ROC. And again, as I mentioned, if we don't have the ROC mentioned, we have to take all three cases. Also, for a differential equation solution through Laplace transform, if ever you have asked to verify that whether the solution verifies the initial conditions. I told you how to split the solution into zero state response and zero input response, and how to verify your solution if asked. The transfer function HFS is an important tool for analyzing certain properties of the LTI system. So if the transfer function is a rational function, the roots of the numerator will be termed as the zeros of the transfer function, and the roots of the denominator will be termed as the poles of the transfer function. The number of poles and zeros in a transfer function is always equal. So if, say, the order of the numerator is less than the order of the denominator, then the rest of the zeros of the transfer function will be at infinity. And say if the order of denominator is less than the order of the numerator, then the rest of the poles will be at s is equal to infinity. So except for a scale factor, a transfer function can be completely defined through poles and zeros. We learned how to draw these poles and zeros in the S-plane, where the poles and zeros at s is equal to infinity are not drawn obviously. But the poles, we saw that the poles are very important, because based on the location of the poles, we can always derive our ROC from the location of the poles, and based on the location of the poles and hence the ROC, we can say whether a function is causal, stable, or invertible. For example, how the properties of LTI systems are determined through transfer function. For instance, causality. We saw that for a causal system, if the ROC is such that it is towards the right of the outermost pole, given the order of the numerator is less than or equal to the order of the denominator, that is a proper fraction. So if the ROC is outside the outermost pole, then it's a causal function. Similarly, for stability, we saw that if the ROC contains the g omega axis, then we have a stable system. We considered a special case which was for a causal and stable system. So we saw that for a causal and stable system, the real parts of all the roots must be negative, or the roots must lie in the left half of the S-plane for a stable causal LTI system. Finally, we discussed how to design an invertible system, and we saw that using the properties of convolution, an invertible system is such that when it is connected in cascade with the original system, the transfer function of both these two get multiplied and we get 1, which means that the impulse response of an invertible system is equal to 1 by h of s. Finally, we used Laplace transform for simplifying system function algebra and making block diagrams of an LTI system. Firstly, using the properties of Laplace transform, we saw that how can we simplify system interconnections. We saw 3 system interconnections. Firstly, the series or cascade connection, and using the property of convolution, we saw how a series or cascade connection can be combined into a system which is a product of all those, which is a product of the transfer function of all those individual systems. Similarly, for a parallel connection, we saw that the overall transfer function is equal to the sum of the transfer function of the individual systems which are connected in parallel. And for a feedback connection, through question numerical which was given to us, we saw that how can we simplify the system, the transfer function of the overall feedback connection of the feedback system. We used the first 2 properties to make a block diagram given a differential equation. We saw 3 ways to make a block diagram given the differential equation. The first form was a direct form. In the direct form, we implemented the differential equation in 2 ways. in the first way, which was a direct form one, we saw that how can we implement the system in cascade in such a way that the pole part is implemented later and the zeros part is implemented earlier. So it is a cascade connection of the zero system and the pole system. In direct form 2, we saw that how can we simplify our system by using a minimum number of integrators or blocks by implementing the pole part first and the zero part afterwards. We used integrators for reasons we know that integrators, why are integrators easier and better to implement than the differentiators. Then in the cascade form, we saw that how can we break the given transfer function into simpler, smaller first order transfer functions and implement the system in cascade. We saw that in cascade there are multiple implementations possible for a single transfer function and all of them lead to the same transfer function, so any one can suffice for us. Similarly, in the parallel form, we saw that the transfer function can be broken down into a sum of transfer function using partial fraction expansion, and each of the system can be implemented as one whole system. Again, a parallel form can have any one block implemented on first and any block implemented in the second branch or any block implemented in the third branch. All of these parallel forms will give us the same system. We saw that given the transfer function for a differential equation, how can we express the result in the form of xt and yt? How can we convert from the block diagram into the simple form of xt and yt? In the end, we can summarize that the Laplace transform is a powerful use which is used in different areas of mathematics, physics, and engineering. It has lots of applications. For example, whenever we are sending signals over any two-way communication medium, we analyze those signals using Laplace transform. We can study and design process control systems. For example, the feedback connection is a simple example where we can control a process through using Laplace transform. It's easy to design a system using Laplace transform rather than designing a system in the time domain. We can analyze heating, ventilation, and air conditioning systems. Also, it is simple to calculate system modeling calculations. So the calculations can be simplified, the mathematics can be simplified. The mathematical analysis of mechanical systems such as vibrations in spring, flow monitoring in tanks, etc. All of this analysis can be simplified using Laplace transform. Differential equations occurring in the analysis of electrical or electronic circuits, for example, using resistors, capacitors, inductors, and op amps. All of these calculations become simple if we use Laplace transform, as we saw when we were using this convolution, and also when we were just trying to solve differential equations. We know that differential equations actually represent an RLC circuit, or they represent an RLC. Not actually, they can be other circuits which can be expressed through a differential equation, but RLC circuits are also represented through differential equations. So solving them becomes easy if we use Laplace transform. Similarly, the circuit of an op amp can also be analyzed through using Laplace transform. So calculations become easy. The applications of Laplace transform for continuous time system are even exist in further fields of science, for example in economics, etc. So it's an important tool and we must know how to apply it for our course. I'll insist that you go through the ROC, properties of ROC, so that whenever you are determining the Laplace transform of an expression, you are able to deduce the properties of the system using ROC. That is all. Wishing you all the best for your course. Thank you. Allah Hafiz.